Hello guys, welcome back to Maison African Motives, still on power machines and 5, working on revisions on governance. In this case, we have got a question that is from April 2023 exams. That was question 5.2, which was referring to a porter governor in this case. So we are given that 287.5 millimeter long arms of a porter governor are fitted to the axis of rotation. The rotating balls each have a mass of 1.9 kgs, rotating at 100 revs per minute. And the central load is 8 kgs. The arms form an angle of 30 degrees with the vertical. The sleeve movement is plus or minus 25 millimeters. Calculate the sensitivity of the governor. That was 9 marks, okay, which is a lot in exam. All right, anyways, let's just take the information that we are given in this case, that is the data that you're given. We are given that the arms of the porter governor, so in this case, I'm going to refer to the length of this as L, okay, which is given as 287.5 millimeters, which we can write it to meters. Remember, 1 meter is equal to 1,000 millimeters. So you can divide by 1,000. This is going to give us 0.2875 in meters. Also, we are given that this porter governor, it is fitted to the axis. The rotating balls each has a mass. Remember, guys, I told you that the mass of these rotating balls is the small letter M. That is the one that represents the mass of the rotating balls. The capital letter M is the mass on the sleeve. That is the mass of the central dead load, okay? And rotating it, so given the speed in revs per minute, that is N. So N is the one that is measured in revs per minute. So we are given 100 in revs per minute, okay? Which can be converted to rad per second. Remember, the question here is to work on sensitivity, to calculate the sensitivity. Okay, so there we need actually the mean speed, this speed, which is our mean speed in this case. So this mean speed is supposed to be in revs, in rad per second. So you can convert to rad per second. Remember, in rad per second, omega is equal to 2 pi n over 60. That is the n in revs per minute. So we can convert this, which is 2 pi times n, which is 100 over 60. So you can actually convert and have your omega in rad per second. So this is going to give us 10.472 in rad per second. So let's leave it like that. We are also given, and the central load, that is the central dead load in this case, has got 8 kgs. So we are given M, that's capital letter M, which is 8 kgs. The arms form an angle of 30 degrees with the vertical. These arms, which are 0.2875 meters, they form an angle of 30 degrees, so that we can just write it as theta, which is 30 degrees. Then the sleeve movement, so in this case, the sleeve movement, I'm just going to refer it as D, okay? You can just use any letter of your choice. So in this case, as for me, the sleeve movement, I'm just going to represent it with letter D. So D is equal to plus or minus 25 millimeters. So since we wrote the length of the arms in meters, so you can also write this movement in meters. That is, you divide by 1,000, since 1 meter gives us 1,000 millimeters. So this is going to give us plus or minus 0.025. That's 0.25 in meters. Okay, so this is the information that you're given. The question is, from this information, to calculate the sensitivity of the governor, which is the porter governor. Okay, I'm going to write the formula that you need if you're dealing with sensitivity for governors. We know that the sensitivity is given by the formula that is, okay, let me just write it here. So the sensitivity, that sensitivity in this case is equivalent to the mean speed. So this is given by the mean speed, which is the omega, okay? Everything over the higher speed minus the lower speed. So you're going to use the higher speed in rad per second. Everything is in rad per second, okay? Minus the lower speed. So usually the lower speed is at H2 when you are dealing with the second one. The higher speed is when you're dealing with the first height. Okay, I'm going to explain that later on. So this we can write our formula as omega over omega 1 minus omega 2 like this, which is measured in rad per second. So this is the formula to calculate what? Sensitivity in this case. All right. So our sensitivity is taken from the mean speed, which is our omega, which is the one that we have here. We have our omega from this information, from the data that we are given. We obtained our omega here in rad per second, but we do not have these other speeds, which is the omega 1 and the omega 2. So how are we going to obtain these values, omega 1 and omega 2? Okay, this is the idea that happens if you are dealing with a Porter, let's just check here, it's a Porter governor. All right, so if you are dealing with a Porter governor, let's just have a scale so that you understand what we have. I think these formulas, they are fine. Let me write it above this so that we can just refer to this information. From the movements that were happening in this case, we had a sleeve movement. So this movement that is going to affect our omega 1 together with the height that is going to be taken from this angle of 30 degrees. So how are we going to have that one? Okay, normally our governor is supposed to be like, I'm just going to have a sketch of what you are supposed to have. You are supposed to have something of this nature from our Porter governor. All right. So we are going to have, in this case, I'm just going to work with one ball. This is the ball that we have. All right. So this is going to be like this to the horizontal. Okay. So this part you're just supposed to know, just a basic part of your governors, guys. All right. So you're having something of this nature, depending with the textbooks that you are using. All right. So in this case, this is the ball that we are having here. I'm just indicating this ball here. All right. So we are given that the mass of this ball, we have the mass of the ball, and we are also given the mass of the sleeve where we are having our sleeve. So in this case, here we are going to have our mg over 2. So this is also to the horizontal. So we are going to refer this to the horizontal. Okay. So if we are referring this as the horizontal line, it means we are having a height here from this point to this point is the height, which is the same as the height that was taken from this point here. This point here, this is your height. So this is your height. This is your height also. But these heights, they are going to be determined by the sleeve movement, which is that D that I referred to. So in this case, we are given this as the angle between the arm. This is an arm, and this is the vertical movement, the vertical line. So the angle between this is your theta in this case, which is the 30 degrees that you are given. We are given that there is an angle of 30 degrees. So this is the one that you have in this case here. So we are going to indicate this as our 30 degrees. But I want you to check something from your mathematics. You see that this is a vertical line also. This is a vertical line. This is actually a straight line that we are having. You are having a straight line. So it means this angle and this angle here, they're actually the same. From which concept? We are referring from our Z angles, which are alternate angles. To say these two angles, they are equal. So if these two angles, they are equal, it is going to help us to calculate this height, because we are saying this height here is the same as this height that we have here. This is the length of the arm, which is the one that we are given. We are given here the length of the arm here, which is L. So we are given L, and we are also given the angle. So which means we can calculate this height, because we need this height to calculate the speed. All right. From those speeds that we have, we need this height. Okay. Why am I actually referring to this height? Remember that from this formula, the mass of the sleeve, the mass of the balls plus the mass of the sleeve times the gravitational acceleration is equal to mw squared h, which is the omega times the height. So the height here, they are going to be differentiated due to what? The sleeve movement. So that is why here we are having omega 1 and omega 2. So which means we need to calculate H1, we need to calculate H2, which is going to help us now to calculate omega 1 and omega 2. So that's why I am focusing on this height, on how you are supposed to calculate the height, so that it is going to help you now to calculate those speeds. Okay, so according to this triangle that we are given, we can play around this triangle to calculate any. Sometimes maybe it's a question which needs the radius from this point to this point. This is your radius. You can also calculate your radius from this condition. All right. So you can also calculate your radius. So meaning to say, if from this triangle, since it is a right angle triangle, according to this theta that I'm given, okay, there's an angle which is inside the triangle, this one. So according to this angle, this side that has got H is our adjacent. This side is adjacent. Here we've got 90 degrees. This R here is your opposite, which is in this case, we are not focusing with this, but in case you want to calculate it on another typical question, but in this case, we need to calculate H. So we are supposed to focus on the adjacent and on this one, which is our hypotenuse, that is the length of what? That is the arm, this one, which is our L, which is your hypotenuse. So from your trigonometrical ratios back to your mathematics, there is only one ratio that has got adjacent and hypotenuse at the same time from your SOHCAHTOA. So that is from our SOHCAHTOA. We understand that only one ratio is got adjacent and hypotenuse, which is for cos. So it means the cosine of theta, which is the cosine of 30 degrees, is equal to the adjacent over the hypotenuse, which is the adjacent, that is your H, over the hypotenuse, which is the length of the arm in this case. And we have this length of the arm, which is 0, so we're given the length of the arm, which is 0,2875 in meters. So you're going to calculate your H from there. So meaning to say, from this information, we can calculate H by cross multiplying, guys, for back from your mathematics. So 1 times H, this is H, which is equal to 0,2875, the cosine of 30 degrees. So that means we are going to have H in meters, since we used the length of the arm in meters. Okay, so our H in this case is going to give us 0,249. If we round off to 3 decimal, please, was 0,2485. So it's going to be 0,249 in meters. Okay, now you have the H. Let's get back to our formula now, and that we wrote about, that we talked about before. Remember, I was saying H is going to help us here to calculate this sensitivity, since we need omega 1 and omega 2, which are taken from this formula. So we have our H. So that H, we are not yet done. I just want you to remember the formula, so that when you are now working on the formula, we won't go wrong. All right, so remember we said in this case that our mass of the balls plus the mass of the dead load times gravitational acceleration is the same as the mass times omega squared H. These two, they are equal. So in order for you to calculate omega here in this case, this goes to say, if you are working with the speed, the first speed, which is omega 1, you are going to use the height that corresponds to that speed. Meaning to say, if you are to calculate this omega 2, you are going to use your formula now as the mass, that is what the mass of the balls, the speed squared that we have, H2 is equal to m plus mg. So this is what you're going to have in this case. Meaning to say, this formula is going to help us to calculate omega 1 from H1. This formula is going to help us to calculate omega 2 from H2. So you can make omega 1 the subject of the formula, or you can just substitute your values direct. But as you can see, the whole part we have from the information, the G is the gravitational acceleration, the mass of the dead load, the mass of the balls, we do not have H1. We have H, but we do not have H1. We calculated H here. So how are we going to determine H1 from this H? Okay, this is what you're going to do. That is the part where you are going to apply the sleeve movement. The movement, there is a plus or minus in the movement. So which means the plus is going to be added to H. The minus is going to be subtracted from H. So that is the idea for you to calculate now the H1 and the H2. Okay, so in this case, maybe let me try to just write it aside so that it can help us. So in this case, we said our H is 0.249 meters. Okay, we saw how to calculate H. So let me just remove this part. Also, this omega, we saw how to calculate omega. I'm just going to write my omega here, which is 10,472 rad per second. Okay, we saw how do we calculate this one, so it's fine. Now, like I said, due to the sleeve movement, there is a plus and there is a, which means we are going to add or subtract. So H1 is going to be this, when the sleeve movement where you are going to subtract. So this is going to be taken this way. H1 is going to be given as the height that we had before, which is H, minus the sleeve movement over 2, which is the average. So you use the average value, D over 2. So that means H1 is equivalent to H, which is 0.249 minus D over 2, which is 0.025 over 2. So this is going to give you H1. So H1 in this case, if we are to simplify properly, we are going to obtain 0.2365, something like that in meters. Okay, so that's your H1, which is from the same calculation or from the same way that we did. Now we can calculate H2 because there is a plus or minus. So the minus part is for H1, the plus is for H. So our H2 is going to be taken as H minus, that is a plus this time, so it is going to be plus D over 2. So that means H2 is going to be H, which is the same thing that we had before, 0.249 minus 0.025 over 2. So this is going to give us our H2 in this case. So our H2 calculated is going to be 0.2615 in meters. So we have H1, we have H2. All right, so these are the values that we have been actually limiting us all along to calculate these speeds, which is omega 1 and omega 2. So since we have these values, we can substitute into this formula everything that we are given in this case. All right, so in order for us not to confuse, let me take this formula as it is. This part that we are given here, I'm just going to rewrite this formula as it is so that we do not confuse. I'm going to write it where we have got our values, this formula as it is, so that we can calculate omega 1, then we can calculate omega 2 again. So we saw that from the formula that we are given, we can calculate these values, omega 1 and omega 2. So also I can just remove this diagram. I don't think now we can need this. We saw how to use the diagram. So let me just remove this diagram, guys. Sorry for that. All right. So now from this information that we are given, we want to calculate omega 1 and omega 2. So from the formula I wrote before, okay, I already have this one here. Okay, so let's have it as on this one. So I'm just going to start with this side here, this one. All right. So that's M omega squared H is equal to the mass plus the mass times the gravity. So this is what we have. So in this case, like I said, if you are calculating omega 1, you use H1. So it's either you can make omega 1 the subject or you can just substitute your values there. Okay, let me show you how you can make omega 1 the subject. You can divide by M and H1 both sides. So that means here we can divide by M, H1 both sides. M, H1 both sides, M, H1 both sides. This can cancel. So that means we are going to remain with omega 1 with a square. So in order for you to remove this square, you are going to introduce the square root on both sides. So this is going to be having a square root. So it is going to be mass of the balls plus the mass of the dead load over the mass of times this gravitational acceleration, mass times what? The height, 1. So on a condition where there is no frictional force, because we shall talk about another part where there is a frictional force, where you subtract the frictional force on top. But in this case, we do not have that condition of a frictional force, okay? So we can calculate our omega-1 in this case. So therefore, or you can substitute direct into the formula, the one that you had. If you understand it, you substitute direct as it is, or you can use this one, then you can calculate omega-1. That's omega-1 is equal to the square root of m plus m. This is m, the mass of the balls in this case. So in this case, we've got the mass. Okay, let me increase again a little bit. Okay, so we have got m here, the mass of the smaller letter m. That's the mass of the balls in this case. Let me write in this case. All right. That is the rotating balls, and this is the dead load, which is the sleeve in this case. Okay, so we have got m, which is 1,9, plus the capital letter M, which is 8, over the small letter m for the balls again, which is, okay, let's just finish on top before we confuse each other. So that's times G, which is 9,81. Everything over the mass of the balls, in this case, the rotating balls, which is 1,9 times H1, which is the one that we calculated here, H1. So H1 is 0,2365. So this is going to give us omega-1, which is measured in rad per second. Remember, omega is rad per second. So that's something like 14,701 in rad per second. So we have omega-1. With the same formula that we have, we can calculate our omega-2, because we are given that if we are calculating omega-1 from this formula, it means omega-2 also can be calculated from the same way or from the same consideration, because omega-2 goes with H2. So here we are going to write H2. So it is going to be equal to the square root of the mass of the balls plus the mass of the dead load times gravitational acceleration over the mass of the balls times H2. So this can give us omega-2 in this case, which is going to be, this one is a repetition as it is, 1,9 plus 8 times the gravitational acceleration 9,81 over the mass as it is 1,9. The only thing that changed is H2, which is this one, according to that sleeve movement that we talked about before. So that will be 0,2615. All right, so you can have your omega-2 in this case, which is going to give us 13,981 in rad per second. Okay, so in case you have confusion to say, what if I calculate my H2 as H minus D over 2? That one is not a matter of fact. Maybe you have a confusion in exam. You calculated, you vice versa these values. That one is not a matter of fact, because remember, on our formula for sensitivity, this one is, if you use it this way to say sensitivity is the mean speed over the higher speed minus lower speed, then if this is, maybe you vice versa your values, this is omega-1, which is 13, this is omega-2. Then you choose which one has got the bigger value between these two. That is the one that you use. That is the higher speed minus the lower speed. So in this case, depending with your calculation, but sometimes you can just vice versa these values. Then you see, okay, which one is got the higher speed? That's how you can actually attempt this question. So therefore, our sensitivity in the final can be calculated, which is equal to the mean speed, which is our omega, the one that we calculated before from our n. Remember, our n in revs per minute gave us 10,472 in rad per second. So that's 10,472. So this is going to be 10,472 over omega-1 minus omega-2. So we are now dealing with those speeds, which is the higher speed minus the lower speed, according to these values that we obtained here. All right, so this was our omega-1, which the higher speed, omega-2 with the low. Remember, omega-1, this is 14. Omega, this is 13. Omega-2, which is 13. So 14 is bigger than 13. So we are going to start with omega-1, which is we subtract these two speeds. All right, so that is what you're going to have on your final answer. So you're going to subtract the two values, that is your omega-1 minus omega-2, which is going to be 14.701 minus 13.981, the values that we calculated. So this is going to give us sensitivity measured in rad per second. All right, so that's your sensitivity in this case, which is going to be 14,544 if you round off to 3 decimal places, which is in rad per second. So as you can see, this whole question is having 9 marks, which is a lot in exam. So you have to be very, very careful when attempting typical questions of this nature, because the information that you're given is the one that matters. Sometimes we need to subtract the frictional force if you are given the frictional force. I shall talk about such considerations, but for now, for this one, it was just a matter of manipulation of the formula. So like I said, you can also calculate your omega-1 and your omega-2 from this formula. You can just substitute the direct, because you know that omega-1's H1 is equal to mass of these balls plus the mass of the sleeve G. So you can substitute your values, the omega, the mass, this one and this one, you substitute everything, then you make omega-1 the subject, whilst you are calculating, still you obtain same values or same answers like the one that we had. What is important is the application of the formulas, how to use your formulas properly. Okay, that's it, guys, from Mason African Motives, working on power machines N5, till we meet again.